Welcome everyone to the August 4th OMR Architecture Meeting. Today we have one topic from Devin Papineau. He'll be talking about some profiling tools for profiling JIT scratch memory. So turn it over to Devin. You can take it over.
Okay. So I'm just going to share my screen. Share. Is my screen going to show up? Well, that's fun. Okay, I'm gonna click on this, and then we'll see if anybody can see anything. It looks like it's just a cursor on a black screen, as far as I can see what it's sharing.
Yeah, that's what it looks like.
Okay. In that case, it looked like it was going to work to share individual windows, which is less convenient, but here, this one. Okay. Can everybody see that?
Yes.
Okay, great. Now, so I don't have any slides, so I'm just going to sort of talk about it, and then show what I have. So the context here is I've been trying to look into some very expensive compilations, both in expensive in compile time and in scratch memory usage. And some of the scratch memory usage is just it's through the chart or off the charts, through the roof. So we do have some existing stuff that will try to tell you about scratch memory usage. In particular, we have a type called region profiler, and there's also one called lexical mem profiler. And the problem that I have with them is that they don't really work in the way, like they don't give me the information that I would hope to see. And the reason for that is that they're, well, I guess what it is that memory is, unlike time, it's reusable. Which means that you can't just accumulate all of the usage and look at the total, right? Like we're not interested in total memory usage, we're interested in maximum memory usage. So these existing things, they accumulate across the run, but that's not telling you what memory were we using when we were at an interesting maximum point. So in order to try to find that out, I've been working on this tool. So basically, there's different instrumentation to measure the memory. So here, there's something here that says profile this scope. It's going to declare a variable with this name, and we will call the scope opt in the output. And this is going to interact with all of the stuff that I've been working on, and basically, it's going to record a detailed stream of events during compilation. It's going to generate this output file with, this happened, this happened, this happened, this happened. In particular, The interesting events are we've got the start and end of compilations, and then within a compilation, the creation of a region, destruction of a region. Here I mean TR region, the memory region. At the start and end of a scope like this, right? So the start is here where the line is, and the end is when this variable goes out of scope at the end of the method in this case. And allocations within the regions. So, you allocate an object, and that's this many bytes and whatever, and then that gets counted. And then now, instead of recording every single allocation, I treat all of the other events as sort of significant points in time, and I just sort of total the allocations in between them. And it's there'll be like sort of a linear approximation between the significant events later on. So then this event stream, it's got a lot of data that can answer questions, right? So we can do post-processing on that data to find, what it is that we really want to know. The other thing is that as I was doing this, I realized that if I timestamp the events, I also get sort of how much time was spent in each scope for free. I wanted the timestamps because I wanted a graph of memory usage over time in roughly actual time units. Okay, so and I guess I'm hoping to supersede and displace these existing, the region profiler and the lexical mem profiler, and I guess there's also a lexical timer that would hopefully be unnecessary if supposing that everyone is sufficiently interested, or let's say doesn't object. So right, that brings me to, let's see it working. Okay, make sure I have my right Java here.
Can I just ask a clarifying question, maybe just for?
Sure.
So you have to go and so tr underscore profile scope is something new that you are introducing. So you have to go throughout the code and drop those into all the places that you want to be able to profile.
Yes, they do need to be sprinkled into the code by a human.
Okay. Yep.
Okay, so here we go. If you have a big enough resource usage problem, and it's repeatable enough, so with things that I've looked at so far, I've found that I can say, oh, I want more detail about this, and then I can go add it into the code and rebuild, and then rerun. So where exactly the things should exist all of the time versus should I have some that are behind an option, and maybe you tack a boolean onto here or something, versus which things should be left to a process like what I just described. That's sort of an open question. Right. Okay, so I'm going to be using Java here, but basically none of this is Java specific. The the implementation is almost entirely in OMR. I think I've got some something about the getting the timestamp, where we want to use the OMR port lib, which we can't rely on being able to directly call from the JIT at the moment in OMR code, but we can in a downstream project. And so I'm sort of doing an end run around that, but this is it's basically all OMR level stuff. Okay, so all right, so we're gonna run version, right? And in there we can specify, first of all, I'm gonna make it, spend some time actually actually compiling async compilation. Let's tell it to do hot, low count. So that's going to actually spend time. So now, in order to collect profile, so the option called profile compile scopes. And here it tells us you need an output file name. So we can do that. Call it version.data. And if I run that, it shouldn't take too long. Here, we've created an output file like this. Now, before I go on, I'm just going to delete that and generate a new one. I want to sort of highlight, this is each compilation generating this stream of events. So each one naturally has its own output. We'll suffix logs now too, so that we don't have to deal with all the junk on the end of that. So if I run this and then I just cancel it, we see here's a thread specific output file. And this is what has basically the data in it, right? And if we had more compilation threads running, there would be more of these. And the file that we specified, if we look at it, it's just listing the name of this. And then on JIT shutdown, it combines them all together. So sometimes you might have a case where the the process, it didn't shut down in the normal way, right? Something like this happens where I just canceled it, or I know we've had at least one benchmark that we cared to look at before, which ended with the process being just sent a sig kill for some reason. So if that happens, there's an option to combine an existing one. So it's is it scope profile combine? I'm forgetting my own option. Options. Scope profile combine. So scope profile combine. Then you give it this thing. And now it's been put into the main file. So this is because transporting multiple files that go together is not fun. And interpreting file names across different operating systems, and is it an opaque byte string? Is it a sequence of 16-bit things that are kind of UTF-16, but not totally, but also it's case insensitive as though it's UTF-16, and all this. So that's what that's about. So now I'm gonna rerun this and just let it actually finish once again, and then I can show you what we can see inside of that. I guess I can talk a little bit about what we can see inside of that while it's running. Well, it's done. All right. So I guess the main thing is the memory, but let's start with probably the time at the moment. So there's a tool that I have here in this directory. Well, and I guess first of all, if you look in here, it's a Python script, but it relies on this C program next to it because tearing through the data in Python, I originally tried to do that, and it took minutes to open even a modestly sized profile. So this is a C program. The script will compile this, feed this the data, and then this will generate an output file that then the Python operates on. And this is going to use matplotlib to show everything that it's showing. Right. So now I can actually run it. Pass that version.data. How much data did we actually collect? 20 megs. When I run that, we get a list of everything that we have profiling data for. So this is how you pick it out from the list, right? It asks you to choose which one. This is the peak backing memory usage for scratch memory. It's the total amount of time that it took, and the op level and the signature. And these are sorted by scratch memory usage. So if you look at the memory usage here, it's increasing. The time is not increasing. You see it goes back and forth. But you can just type in time and you get them sorted the other way. So now the time is increasing here. And the memory usage, see, this one used less memory than that. But I believe the top one is used the most of each anyway. So we can take 0, which is the default. And now it's in a different window, so I have to let's see. Application. There. Can everybody see that?
Yep.
Great. So sorry, brief interruption. Okay, now, okay, so first of all, here's the timeline of everything that we did during the compilation. So we spent most of our time in the opt. That's this one right here. here we have cogen, and you can sort of zoom in. So you can see, that's when we started cogen right there. And if you click, here's the things that we did inside of cogen. We
What
did
is the y-axis here?
so that just shows the nesting.
Okay.
So instruction selection happened nested within the cogen scope.
Okay.
Dynamically nested, anyway. It's not a lexical thing, if that makes sense, right? It's sort of like it's like an activation frame for a function, but it's this scope instead. So it's sort of, you can see the stack, right? We were compiling, we did cogen, we did instruction selection. And you can see how much time we spent. The instruction selection was 16.5 milliseconds. These percentages here, that's the percentage of the parent, and then the percentage of the overall total amount for the compilation. And you can, there's a lot of stuff here that's, it's too small to see, but you can zoom in on that stuff if you want. So this was what, local CSE, loopstrider. Loopstrider did use defs, and then it did its perform method, and so on. So you get, like, this is every time. It's showing you absolutely every time that it entered and exited a scope in here.
So the 2% that you were showing when you were hovering over one of those boxes, one is the percentage, the relative percentage to like the row beneath it, the box that it's in, and then the other is the relative overall.
Yes.
Okay.
Right. You have relative to the parent, relative or sort of like proportion of the full time, and then you have the actual absolute measurement.
Mm-hmm.
You can also, say here's inlining, and this is ILGen, and you can say, okay, well, what were we really measuring when? Oh, you know what? That's not going to it's not going to show up. I'd have to switch windows again. Anyway, so it tells you where the thing is, and you can there's a hook, so you can right click on this, and it'll open it in your editor if you have a script to do that from the file and line number. Right. So there was a lot of stuff going on here, right? Like there's tons of things that we did, and you can see all of it. Okay, so then from this, if you merge together the stacks that are the same, you get the flame graph. So this is just the same stuff, but it's been sort of aggregated up, right? So if we see here, here's GVP, 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 GVP. And then this is the total of all the GVP. Right, so you can see 5% of all the time here was spent doing value numbering for GVP. Oh, here, yeah. So here you can see there's also a total versus self. So it only shows that when it actually looks different. And the self is just the time excluding any of the children nested inside. So that's this is basically just a flame graph like the Brendan Gregg script online. But it's derived from this event stream. Okay, then, the star of the show here is the memory. So this is scratch memory usage over time. So you can see these linear approximations here, right? You get to end up with this straight line. And it's just that, there wasn't necessarily any interesting events along there. Anyway, this is, how much memory we're using over time, and it measures, well, it shows a whole bunch of stuff here. So first of all, this is a stack plot, right? So the blue at the bottom here is the heap memory usage for the heap region. The orange then is the node pool region, and then CFG regions, structure regions, alias regions, and so on. And then at the top we have this yellow is the stack regions, which is mostly stack memory region, but it also includes some that are not registered as a stack memory region, but are declared on the stack for a relatively short time, which happens in a few places. And so in here we can see, this right here is clearly where our peak memory usage is, right? Oh, I forgot to say, right, there are 3 different ways in which all of these amounts are measured. So we're looking right now at requested memory. So when you say, region.allocate 12 bytes, the requested memory is 12 bytes. So that's just, it's just what was asked for. Then there's allocated memory is higher. This is the amount of memory that we sort of had to burn in order to give you the requested amount of memory. So part of that is if you asked for 12 bytes, we need to stay aligned, and so we give you 16. Or well, we give you 12, but the 8, or sorry, the other 4 is just lost. It also counts if you're in a region and you're near the end of the segment. So let's say you have 100 bytes left in the segment, and somebody asks for 108 bytes or something. Well, you're going to get a new segment, and you're going to hand them the 108 bytes from the new segment, but then nobody ever uses that 100 bytes at the end of the original segment. So that's counted as allocated here, right? It's extra wastage that we had to burn in order to satisfy the allocation request. And then finally, there's the backing memory, which is just the total size of all of the segments that the region has taken from the segment provider.
Devin, can I ask a question?
Sure.
Maybe I missed it when you first started showing this graph. Is this just one method, or is this of all compilations?
This is one method. Okay. So because of the reusable nature of memory, it doesn't make sense to aggregate across all the compilations.
Okay.
Right, like if you now there's something about like which things were happening simultaneously with which other things. And that's a kind of information that I haven't tried to capture here. But at a coarse grain, we have some number of compilation threads, and each of those can at any moment be using up to the maximum that we used for any compilation. but that maximum memory usage it's bounded by, the it can't be any more than the number of compilation threads times the max in a single compilation. And right, so this is exactly the same reason why I'm not adding up all of the allocations even within a compilation, right? Because, well, after this point, maybe all of these, I think these correspond to the GVP. And maybe if you add these up, they might look like they're just as much as, or nearly just as much as this thing. But really, they're far less of a problem than this thing is, if that makes sense.
Yep.
Okay. So those are the three kinds of memory that we've measured. And so I'll go back to requested. So when you look at requested, it shows the gray is sort of the top of where the allocated memory would be, and the pink or the sort of transparent red is where the backing memory reaches up to. All right, so what we could do with this now, so you can zoom, and you can look very closely if you want. And this x-axis is tied to the timeline, so you can see what part of what you were doing at the part in the graph that you're looking at. But probably more interestingly, we can select a range of time like that, and it will identify the peak memory usage within the selected range. Or you can sort of double click to select the whole thing. And so here's our peak memory usage, right? So we want to know what was going on. Now, part of it, it's not too hard to tell. From looking here, we see that we're at the end of PRE. But having identified this peak, we can sort of go inside to look at it. And here, it's able to reconstruct all of the regions that exist. How much memory is allocated in each. And so these are the same categories that were shown here on the in the stack plot, but now they're a bar chart showing, again, requested memory, but you can look at allocated or backing. And the relative size of each region, so each region is drawn as a separate rectangle within these bars, with the area proportional to the size of this measure. You can't really zoom in on these though, not like this, right? Because it would change the aspect ratio, which changes the meaning of the area, and then you wouldn't necessarily be looking at what you thought you were zooming in on. But you can sort of and do that to sort of fill the screen with one category. Then we can tell, if you hover, it'll tell you exactly the size of that. This one is 20.6. This one is 57.2 megs. These percentages are, it's the percentage of the category and then the percentage overall. And when it says region number whatever, that's just the index of there were 16,364 regions created before this one was created. You can also look at the look at this by number of regions. So rather than sort of the size of memory allocated within regions, you can look at just counting the regions. So here you can see that we've got just absurd numbers of CFG and structure regions. And then, oh, I didn't want to go there yet. Spoilers. If I go back to, yeah, here. And then the other thing that we could do is we can select these regions. So, maybe we're interested in, let's say, everything except the heap region. And that tells us that it's, all this stuff is 99 megs, and that's how many percent it is of the total and so forth. Now, from here, we can go into the memory flame graph. So this is just like the time flame graph, but now instead of the width of these frames representing an amount of time, they represent an amount of memory, and this is just memory. It's who allocated the memory that is still outstanding at this exact moment, which is exactly what you need to know if you want to be using less memory at this peak. So we see, 86 megs in partial redundancy elimination. What's this? Inlining, that's not much of the total, but you can sort of zoom and do the same things here. Yeah, so we could see, for example, right, like out here, we can see that it's the stack memory that suddenly increased the most, right? There's a bit of alias or whatever. So you can look at, say, just stack. That's that category. And we see that it's almost entirely partial redundancy elimination doing that. And now if you were to, put some of those, I can't point outside of this window, but if you were to drop some of those profile scope macros into some strategic locations, then you would see further breakdown of who allocated it. And of course, that flame graph is using the measure here of requested memory. But if you were in, allocated, say, then it would show you allocated, right? So this is 85.8 megs, which is the total selected here, which is different from the 83 requested. So that's not too much overhead over here. From here, also, if you look at the count and then you go to the flame graph, right? So now the measure is number of regions, and these are attributed to the stacks that created them. So we can see that these were created mostly by inlining. 1.39 thousand regions created by inlining. So there you have that. And I guess I can show a little bit what happened to ish. It's probably gone because I closed the window, yeah?
Yeah, let's go.
Okay. So if I come back here, see me typing?
Yeah, see your
Great.
terminal there. Yep.
So so here I could look at well, I won't bother running it because you've seen that part, in which case I probably shouldn't have bothered switching to the terminal, but oh well. We can run the same thing on this is here, and we see this one took, a full 4 gigs. I ran with an increased scratch space limit, and if we select that one, oh, by the way, it tells you here the smallest difference in time that it saw between any 2 events that could actually distinguish their timestamps. That's just sort of to give you an idea of kind of the resolution of the time data that this thing is working with. So if it gets too precise, like if you see things that look like they're 1 nanosecond, that's a fiction where it's sort of spread things out in between. In between successive timestamps. And then all of this stuff down here is just sizes of parts of the temporary file. So you wouldn't normally see this. I got to turn that off or put it behind an option or something. Or just get rid of it. Anyway, if we go to I have to keep switching. Here. Okay. So, yeah. So here, for example, we can look at this. This is Alias Memory. And maybe I'll look at the backing. Wow, the backing is way down there. That's interesting. I was seeing a larger problem with Alias Memory before. I'm not sure what's going on, but here we can see like this just absurd number of regions again. This is 122,000 regions. And now I'm not going to go into the flame graph for this because it's slow, and it's slow because of there's just this number of regions is just crazy. And they're basically all CFG and structure regions, so there's definitely something going on there. I think it's good to see this count because one, it interferes with what this tool is trying to do, and two, it could represent a space usage problem of its own because the backing memory doesn't count. There's a 4K buffer that's allocated in line as part of every region object. And it starts with that, and then it only allocates segments if it runs out of its 4K buffer. And I don't want to count that as part of the backing memory because then you're double counting, right? So that 4K buffer as part of the region object will, well, except for possibly the main heap region, it will be within memory that was allocated by a different region. And so that would be double counting. But basically each of these can represent 4K 4 kilobytes allocated elsewhere. Now, I did some investigation using all of this stuff, and I found that that this stuff isn't really holding on to a lot of um, uh, those 4K embedded buffers, basically, because they're allocated within a stack region, and not many of them continue to really exist for a very long time simultaneously, but they are they're not destroyed, like they don't get their destructor called, and so we end up with this is all left over, and we also end up with you know, some amount of backing memory that should have been freed that never was. If we yeah, so I think this way down here is probably the main CFG, and all the rest of this is not needed. And I have some let me see, I probably should have run this in the background while I was talking about that. But let's see. Scratch space limit, da da da. Sorry, you would see what I'm doing. It's the screen sharing problem. But basically I'm rerunning the benchmark that I got this from. So that I'm rerunning that with a slightly newer revision of my code where I've sort of worked around some of these things. But we can see here the aliasing was from global copy propagation. Right, so it's actually still not too slow if I don't select all of this stuff. Anyway, in a moment, the my rerun will complete, and basically I have some changes that I've made locally in response to things that I've found in here. That one is, I think, actually a good change on its own, which is to get rid of all of those ridiculous regions that that are misleading. The other one is sort of a provisional. I don't know. It's sort of a workaround for this here. The copy prop, using a lot of alias memory, which I tracked down to basically the alias set interface using far more memory than it ought to. Okay, it's finishing.
Sorry, how did you go from global copy propagation to alias set interface? You just inspected the code?
No, I kept rerunning with more scopes being measured.
Okay. And then you eventually caught the
Yeah, and then I
range.
found exactly where we're allocating most of that alias memory, or possibly all of it. But those scopes are not in the build that generated this.
Yep. Okay, got it.
Okay, so there, that finished, and So now I will open solve position constraints it was. So again, sorry you can't see that, but back to here. Right. So we can see here that now, first of all, it looks like this one didn't finish. So that's fun. Because you can see at the end here, yeah, partial redundancy elimination goes all the way to the end of the timeline. So something's happening there. But we did not create a gigantic alias spike in global copy prop. And if we look over here, now we only have 24 regions. So this is much easier to look at. By the way, there's this detailed information exists for this method and many others. I guess you saw the scrolling list before. And this output file is 244 megs, which could just be one hot compilation log if it's a big enough method. So I tried really hard to keep the output compact. But anyway, there you have it. Here, there's more detail on what's happening during inlining in this one. You can collapse this recursion when you look at the flame graph. But anyway, that's what I have going here, and hopefully people are interested to have this as part of OMR. It's a considerable chunk of code to make this all happen. I think the C and the Python each in the tools directory are about 3,000 lines. But that's what I have to show.
Okay, great. I mean, I think this is a great improvement over what we have, and I mean, you've already. I mean, in terms of your ability to find where some of these memory allocation problems are, and you've identified a few places. I know you didn't mention them all on this call, but I think that it's really proven its value there. So, getting this into the code and getting it into the hands of other developers, I think would be a very useful tool to have for sure. Very early on, you were talking about lexical memory profiling and lexical timers. Like, we already have functions for that. Are you saying that we could deprecate those and perhaps unify all this under these I don't know what you want to call them, tags that you would add in the code to delimit where this profiling should occur?
Yeah, that's what I was hoping, because it seems redundant now to have the say lexical timer thing.
Mm-hmm.
And it seems kind of worse than redundant to continue to have the region profiler and lexical mem profiler, because they'll just give you strictly worse information, I think, than what this gives you. And those are all things that that do need to be deliberately placed in the code at points of interest. So a lot of the places where I have placed my profile scope macro are places where it's right next to one or more of those other things.
Mhm.
um, and it seems as though those uh, sort of should be unnecessary after.
Okay. Yeah, I would support that direction. Um, the existing TR memory class has got there's a large enum in there where you can specify when you allocate where the memory is, or what phase you're in, or who's going to be using the memory. It's you probably know what I'm talking about. Do you use that information, or is this just is
No,
it
I'm not
sufficient?
using that information. I think a lot of things don't even necessarily specify it. Probably mostly things that are allocated in the heap region specify it.
Yeah, I know we used to be very careful about specifying. I can't remember what that term is. Where the memory is going to be, like who's asking for the memory. At least like 15 years or so ago. But I think that that has definitely not been enforced as much as it used to be. So I think a lot of it is stale. But uh, the reason I'm asking that is because perhaps with an perhaps all of that infrastructure for that could be deprecated as well with the proper placement of these profiling hooks or tags.
Perhaps, yeah. I think in a way they provide like a almost a different kind of information. Like it's a kind of a cross-cutting. Like this stuff is treetops or whatever, independent of who allocated them.
Yeah, that's true. Yes, it's more the structure itself as opposed to who's allocating them. Yes.
So I think I would have to look into.
Also keep track of persistent memory because
Oh,
with
persistent memory. Yeah,
the TR-alloc and related macros, right? They automatically get the enum in there.
yeah, that definitely makes sense for persistent memory. I think because this all this stuff that I've just shown is completely based on region in Scratch
Mm.
Scratch memory. And by the way, it relies on the compilation not leaking any memory at a lower level than region, which we currently have such a memory leak in OpenJ9. I have a provisional fix in my branch, um, but I need to do a proper fix that and do like measure startup and whatever for that. Um, but basically, if region goes out to system segment provider and then out in system segment provider you can leak memory, this won't show it to you because it operates purely at the level of memory regions.
Right.
But I should probably look into how you can even see um, those statistics based on the types that you were mentioning, Daryl.
I think it's
Because I
actually,
don't think I've used them before.
yeah, it may actually be a debug. You have to enable it under debug, like they're guarded with the debug macros. So um, it's been a long time since I've used them, and I wouldn't even rely on them anymore because I think that they are very stale. I don't think that people have been maintaining them.
Mm. Um, I guess one other thing to mention. Wait, I did have another thing to mention. What was it? Hold, sorry, just a moment. Uh, oh yes, the time measurements. Um, you know, you have to bear in mind that it's necessarily perturbed by some amount given that it is instrumentation that is explicitly going off and reading the time and so forth. Although I don't think that that's different from, say, the existing lexical timer. It's just a fundamental property of those of that kind of strategy for measuring how much time you spend in a code section. So you don't necessarily want to have those things be at too fine of a grain. You'll start to not really be able to. It'll at some point you'll have mostly overhead. And also you'll generate a lot of data. Although I did try to make sure that you can put like that you can have a lot of scopes started and ended. I think I put a loop at one point into global VP that just says, okay, well, when we're doing global VP perform, loop a million times, and inside the body of this loop, open and close a scope. And I made sure that didn't produce a ridiculous size file, and that it didn't slow the entire visualization to a crawl.
Mm-hmm.
But still, you don't want ones in there that are not helpful, I guess, or that are at a too detailed level.
Great. Yeah, this all looks good. I think it's a good positive step. Are there questions for Devin? Okay, well, if not,
I take that to mean everybody likes it.
no, it's yeah, I'm very glad to see that we have something like this developing. It's memory consumption is something we really haven't kept an eye on for a long time in the JIT. I mean, there have been cases where yes, we've had to, but tracking it at this level, I don't think we've done in quite some time. So it's a great step forward here. So. Okay, if there's no other questions, thank you, Devin, for taking the time to take us through this and show us what you have. And with that, I guess we can end the call then. Thanks, everyone, for attending this week. We'll talk to you in a couple of weeks. Bye.
Thanks, everybody.